Picture this. It's the year 1147, and you've just burned through your entire inheritance on a bad investment in crusade supplies. Your options are limited. You could become a highway robber, but honestly, you're terrible with a sword. You could try your luck as a merchant, but math was never your strong suit. Or you could knock on the heavy oak doors of the nearest monastery and dedicate your life to God, and accidentally become part of the greatest knowledge preservation operation in human history. Tonight we're diving into the methodical preservation of mathematical knowledge by medieval monks and monastic scriptoriums. Forget everything Hollywood told you about medieval times being nothing but mud, plague, and illiteracy. This is the real story of how a bunch of guys who voluntarily gave up sex meat on Wednesdays and sleeping past 2 a.m. somehow saved mathematics from complete oblivion. And trust me, after hearing what their daily routine was like, you'll never complain about your morning commute again. So before you get too comfortable, smash that like button if you're ready for some medieval reality checks, and let me know in the comments what you think monks actually did all day. Spoiler alert, it wasn't just chanting and making cheese. Now grab something stronger than communion wine, dim the lights like you're in a candle-lit scriptorium, and let's jump into a world where copying a single equation wrong could set back human knowledge by centuries. You're about to wake up at 2 a.m. to the sound of bells. Not your iPhone alarm that you can snooze. Real bells, bronze monsters that could wake the dead, which, coincidentally, is what you'll wish you were in about 5 seconds. Welcome to Matins, the first prayer service of your new monastic life. You stumble out of your straw mattress, which has all the comfort of sleeping on a pile of twigs, because, well, that's essentially what it is. The stone floor is so cold it feels like stepping on ice, except ice would actually be warmer. Your rough wool habit, basically a medieval onesie that hasn't been washed in 3 months, is your only protection against the freezing morning air. The monastery doesn't believe in heating. Suffering builds character, apparently. As you shuffle toward the chapel with your fellow brothers, you can smell everything. The unwashed bodies, the damp stone, the faint scent of yesterday's cabbage soup, that's definitely going to be today's cabbage soup too. But here's where it gets interesting. See, while you're trudging through this pre-dawn nightmare, thinking about how you could have just become a highway robber after all, you're actually participating in something revolutionary. These monasteries aren't just prayer factories. They're the MIT, the Harvard, the Silicon Valley of medieval Europe. And you, my friend, have just accidentally enrolled in the most intensive mathematics preservation program of the Middle Ages. The bell tower you're cursing right now. Its construction required advanced geometric calculations that would make modern contractors sweat. The schedule that's destroying your sleep pattern. It's based on complex astronomical observations and mathematical divisions of time that scholars spent decades perfecting. Even the chants you're about to mumble through while half asleep follow mathematical ratios that Pythagoras would have sold his soul to document. You make it to the chapel, where approximately 40 other men are standing in perfect rows. The precision isn't just for show. Everything here runs on mathematical order. The rule of Saint Benedict, essentially your employee handbook for the next several decades, divides the day into 8 prayer services, calculated by sundial and water clock measurements, so precise that being 30 seconds late earns you a day of bread and water. Fun fact for those watching, medieval monks invented the snooze button's natural enemy, accountability. Your abbot, Brother Theodoric, is already there. He's been awake since midnight doing private prayers, because apparently some people are just built different. He nods at you with that specific expression that says both God loves you and I saw you yawning during Vespers yesterday. The man has been copying mathematical treatises for 40 years, and his attention to detail is legendary. One time he spent 3 days redoing an entire page because a single angle in a geometric proof was 2 degrees off, 2 degrees. The man could spot a crooked line from across the monastery. As you begin chanting, you notice something peculiar about the acoustic design of the chapel. Your voices, even the terrible singers, and trust me, Brother Marcus sounds like a dying goat, blend into perfect harmony. This isn't an accident. The architects who built this place understood sound waves and mathematical resonance better than most modern acoustic engineers. They calculated exact proportions, arch heights, and wall thicknesses to create natural amplification and echo patterns. Every pillar, every curve, every stone was placed according to mathematical principles, preserved from ancient Greek and Roman texts. Texts that, by the way, only exist because monks like you are about to spend the next 16 hours of your day preserving them. The chanting continues for 2 hours. 2 hours. Your legs are screaming, your back is aching, and you're pretty sure Brother Francis next to you has fallen asleep standing up, which is actually a skill you'll develop within your first year here. But while you're suffering through Latin verses you barely understand, something remarkable is happening in the scriptorium just down the hall. Right now, as you speak, Brother Abelard is preparing his workspace for another day of copying Euclid's Elements. He's been working on the same manuscript for 6 months, meticulously reproducing every angle, every proof, every geometric construction with the precision of a Swiss watchmaker. One mistake, one smudged line, one incorrect proportion, and months of work get scraped off the vellum and started over. No Control-Z here, folks. Meanwhile, Brother Wilhelm is mixing ink according to a recipe that involves iron salts, oak galls, and a mathematical ratio of ingredients so specific that being off by a gram ruins the entire batch. The black ink needs to be dark enough to last centuries, but fluid enough to flow from a quill. Too thick, and it clogs. Too thin, and it bleeds through the incredibly expensive vellum. Oh, did I mention the vellum? 1 page costs about as much as a peasant makes in a month. That's right, every single page these monks write on represents weeks of labor for regular people. Drop 1 pot of ink, accidentally tear 1 page, and you've basically destroyed someone's annual income. No pressure though, the morning prayers finally end and you file out in perfect silence. No talking until after breakfast. And by breakfast, I mean a piece of bread that could double as a weapon and watered down ale that makes prison wine look like champagne. But here's the thing, nobody tells you about medieval monasteries, that terrible food, that uncomfortable bed, that mind-numbing routine. It's all by design, not just for spiritual reasons, though they'll definitely tell you it's about avoiding the sin of gluttony. The real genius is that when you remove all earthly distractions, when you strip life down to its absolute basics, the human mind does something incredible. It focuses, it creates, it preserves. These monks aren't just copying books because they're bored, they're creating the most sophisticated information network of the medieval world. Think about it. No internet, no phones, no postal service worth mentioning. But somehow a mathematical discovery in Baghdad ends up in a monastery in Ireland within a few years. How? Through this network of scribes, methodically copying and distributing knowledge like a medieval BitTorrent system. You finish your bread weapon and head to the scriptorium for your first work assignment. Plot twist, you can't actually read. Yeah, about 60% of monks entering monasteries are illiterate. But don't worry, they have a program for that. You'll spend the next 2 years learning to read and write Latin, basic arithmetic, and if you're really lucky, some Greek. It's basically grad school, except instead of student loans, you've taken a vow of poverty, so technically you're ahead of the game. Your teacher is Brother Alcuin, who learned mathematics from a guy who learned it from a guy who learned it from a guy who claimed to have studied in Constantinople. The knowledge chain is sketchy, but it works. He starts you off with something simple. Copying numbers sounds easy, right? Wrong. Medieval numbers aren't your friendly Arabic numerals. These are Roman numerals, and calculating anything beyond basic addition is like trying to solve calculus with alphabet soup. Watch this. Try multiplying xlvz by lx xibs in your head. Go ahead, I'll wait. Give up yet. Now imagine doing that all day, every day, while trying to preserve astronomical calculations and geometric proofs. This is why Arabic numerals were such a game changer when they finally showed up, but we're getting ahead of ourselves. For now you're stuck with the numerical equivalent of trying to code in assembly language. Brother Alcuin shows you how to hold a quill. There's a 47-step process for this, because of course there is. The angle has to be exactly right, or the ink won't flow properly. Too much pressure and you tear through vellum that costs more than your family's farm. Too little pressure and the ink doesn't transfer properly, creating text that fades within decades instead of lasting centuries. He demonstrates on a practice tablet, a wax-covered wooden board that you can write on and smooth over. Think of it as the medieval iPad, except it weighs 8 pounds and gives you splinters. You'll practice on this for months before they trust you with actual vellum. Your first assignment, copy a multiplication table. Not create one, mind you. Copy an existing one, because before you can preserve mathematical knowledge, you need to understand that every stroke, every curve, every number has been standardized over centuries. The number 4 you write today needs to be recognizable as a 4 to someone reading it 300 years from now in a completely different country. This isn't just penmanship, it's the DNA of mathematical preservation. As you struggle with your first attempts, Brother Alcuin mentions casually that the multiplication table you're copying was itself copied from a manuscript that came from Spain, which was copied from an Arabic text, which was translated from Greek, which was based on Babylonian calculations. 3 months have passed since you first picked up a quill, and your fingers have developed a permanent cramp that makes you look like you're constantly ready to flip someone off, which, coincidentally, is exactly how you feel when Brother Alcuin tells you to recopy the same multiplication table for the 15th time because your 7s look too much like 1s. But today something different happens. You're promoted. Not to actual manuscript copying. God no, you're nowhere near ready for that level of responsibility. You're promoted to ink duty. Let me paint you a picture of what this actually means. You wake up at the usual ungodly hour, stumble through matins while calculating how many more decades of this you have to endure. Spoiler alert, it's about 4, and then instead of heading to the scriptorium, you descend into what can only be described as a medieval meth lab. The ink room is in the basement because of course it is. Everything important and dangerous in medieval times happens underground. The smell hits you first. Imagine mixing rotten eggs with vinegar, adding a splash of moldy fruit, and then letting it ferment in a gym sock for a month. That's the romantic aroma of iron gall ink production. Brother Heinrich runs the ink operation, and calling him particular would be like calling the ocean slightly damp. This man has spent 20 years perfecting the exact formula for ink that will last, literally forever. He shows you jars filled with oak galls, those weird ball things that grow on oak trees when wasps lay eggs in them. Nature is metal, folks. These galls are crushed, soaked in rainwater, not regular water, rainwater specifically collected during full moons because Brother Heinrich swears it makes a difference, and then mixed with iron sulfate in proportions so precise, he measures them out grain by grain. The process takes weeks. First you crush the galls with a mortar and pestle until your arms feel like they're going to fall off. This isn't some gentle grinding. You're pulverizing these things into dust, while Brother Heinrich stands over you critiquing your technique. Apparently there's a wrong way to crush oak galls. Who knew? Then comes the soaking. The crushed galls sit in rainwater for exactly 8 days. Not 7, not 9. 8. Brother Heinrich has charts tracking the color changes, the smell intensity, even the bubble patterns that form on the surface. He treats this like NASA treats rocket fuel, because in a way, that's exactly what it is. This ink is the fuel that powers the entire knowledge preservation system. While the galls are soaking, you're tasked with preparing the iron sulfate. This involves taking rusty nails, and I mean seriously rusty, like tetanus poster child rusty, and dissolving them in vinegar. The chemical reaction produces iron sulfate crystals that look like tiny green diamonds. Pretty cool, until you realize you have to handle them with bare hands, because gloves haven't been invented yet, and the crystals stain everything they touch. Your hands will be green for the next month. You look like you've been arm wrestling the Hulk. The mixing day arrives. Brother Heinrich treats this like a religious ceremony, which technically it is since everything here is a religious ceremony, but this one feels extra sacred. The proportions have to be exact. 4 parts gold solution, 2 parts iron sulfate, 1 part gum arabic for binding. Get it wrong, and you've just wasted materials worth more than most peasants see in a lifetime. The moment the iron sulfate hits the gold solution, magic happens. The pale brown liquid turns jet black instantly, like watching a reverse Michael Jackson transformation. Sorry, that reference won't land for another 800 years. The chemical reaction is actually fascinating. The tannins in the oak galls react with the iron to create ferrous gowlet, a compound so stable it literally etches itself into the parchment fibers. This isn't just writing, it's molecular level preservation, but here's the problem. Fresh iron gall ink is actually pale grey, almost invisible. It only turns black as it oxidizes on the page. This means when monks are copying, they're essentially writing blind, trusting that their pale marks will darken properly. Imagine trying to paint a masterpiece while wearing sunglasses in a dark room. That's the level of faith and skill required here. Brother Heinrich shows you the test sheets, pieces of scrap vellum where they test each batch. Some are perfect, deep black lines that look like they were printed yesterday, even though they're decades old. Others are disasters. Brown, fading, bleeding, or worst of all, eating through the vellum. Yeah, you heard that right. Iron gall ink, if mixed wrong, becomes acidic enough to literally burn through parchment over time. There are manuscripts today with holes where letters used to be, like textual Swiss cheese, because some monk 800 years ago added too much iron sulfate. While you're processing this terrifying responsibility, Brother Heinrich casually mentions that the scriptorium goes through about 2 gallons of ink per month. That's hundreds of pages of mathematical treatises, astronomical charts, and geometric proofs, all depending on you not screwing up the recipe. No pressure. You spend the rest of the day learning about additives, wine or beer to prevent mold, because even ink can get infected in these damp conditions. Cloves or copper sulfate for color stability, sometimes gold or silver powder for special manuscripts, though that's above your pay grade, which is 0, because vow of poverty, remember. Each monastery has its own secret ingredients. Some add honey for flow, others use egg whites for shine. It's like ancient trade secrets, except instead of protecting a recipe for fried chicken, you're protecting the formula that will preserve Archimedes' principles for the next millennium. The competitive ink-making scene in medieval monasteries is more intense than you'd think. Brother Heinrich tells you about the great ink disaster of 1089, when the monastery at Cluny mixed a batch that looked perfect but faded completely within 5 years. They had to recopy nearly 100 manuscripts. Several monks had mental breakdowns. One converted to Judaism just to get out of the recopying duty. That might be an exaggeration, but Brother Heinrich swears it's true. Your first solo batch is next week, and Brother Heinrich gives you the recipe scroll to memorize. Not copy, memorize. Writing down the exact formula is forbidden. Too risky. If rival monasteries, and yes, there's rivalry between monasteries over who makes the best manuscripts, got hold of your ink recipe, it would be like Coca-Cola's formula getting leaked. Except instead of losing market share, you'd lose your reputation as a center of learning, which in monastery terms is basically social death. As you're leaving the ink room, covered in green stains and smelling like a Victorian chemistry experiment gone wrong, you pass the vellum preparation area, want to talk about another mathematical marvel. These guys are turning animal skins into writing surfaces smoother than modern paper. The process involves calculus, level calculations about tension, pressure, and drying times. Each piece of vellum is stretched on a wooden frame using a specific amount of tension calculated by the skin's thickness and the ambient humidity. Too tight and it tears, too loose and it wrinkles. The monks use a system of pulleys and weights that would make a physics professor weep with joy. They've essentially created analog computers for processing animal skins. Brother Conrad, the vellum master, shows you a finished piece. It's so thin you can almost see through it, yet strong enough to last 1,000 years. He runs his hand over the surface, feeling for imperfections invisible to the eye. Each sheet is rated on a quality scale that considers thickness, smoothness, color, and flexibility. Mathematical texts get the premium grade because the diagrams require absolute precision. One bump or groove could turn a circle into an oval, completely destroying a geometric proof. The economics of this operation would make a modern CFO quit immediately. One book requires the skins of approximately 300 sheep. A single monastery might produce 5 complete mathematical codices per year. That's 1,500 dead sheep just for math homework, and that's not counting the practice sheets, the mistakes, or the pages. Brother Marcus accidentally used as a handkerchief last winter. Don't ask. By the time you make it back to your cell that night, your head is spinning with numbers. Ratios of ink ingredients, calculations for vellum tension, the geometric principles underlying the manuscript illuminations you haven't even started learning about yet. You're beginning to understand that preserving mathematical knowledge isn't just about copying numbers and formulas. It's about creating an entire technological ecosystem, a manufacturing process so complex and precise that losing even one specialist could set back knowledge preservation by years. As you drift off to sleep on your luxurious twig mattress, you dream about numbers, not the nice friendly Arabic numerals from your future timeline, but angry Roman numerals chasing you through endless corridors while Brother Heinrich critiques your running form. You wake up at 2 a.m. to the bells again, and realize something that would have been helpful to know 3 months ago. This isn't just about preserving the past. These monks are actively improving the mathematical knowledge they're copying. They're adding commentaries, fixing errors in ancient texts, developing new proofs. They're not just scribes, they're peer reviewers, editors, and mathematicians rolled into one. 6 months into your monastic career, and you've finally been deemed worthy to enter the actual scriptorium during working hours. Not to copy anything important. God forbid. You're here to learn the art of ruling. No, not ruling over peasants, though that would probably be more fun. Ruling lines. Making the invisible grid that keeps medieval manuscripts looking neater than your Instagram feed. The scriptorium is nothing like you imagined. First off, it's freezing. Fires are banned because one knocked-over candle could destroy centuries of work in minutes. The only heat comes from body warmth and the occasional ray of sunlight through windows so small they might as well be arrow slits. Which, fun fact, they actually are arrow slits, because this monastery was built during the Viking raids, and apparently multitasking architecture was all the rage. 20 monks sit at individual desks, each angled precisely to catch the maximum daylight. They're arranged in a specific pattern that would make any productivity guru jealous. The senior scribes sit near the windows because their work is too important to risk mistakes from poor lighting. Juniors sit further back, copying simple texts by whatever light filters through. And you're in the corner with a practice board, learning to draw straight lines. The glamorous life of knowledge preservation, folks. Brother Adelard, who you've been watching from afar like some kind of medieval celebrity, is working on something incredible. It's a copy of Al-Khwarizmi's Algebra. That's right, the book that literally gave us the word algebra. He's translating it from Arabic to Latin, while simultaneously trying to preserve the mathematical notation that doesn't quite translate between languages. Watching him work is like watching someone perform surgery while juggling and reciting poetry. Every few minutes he stops, consults 3 different reference texts, makes a calculation on his wax tablet, then carefully adds a single symbol to the vellum. One symbol, in the time it takes him to write one mathematical proof, you could have typed out this entire script on your phone 17 times. But that one symbol will still be readable when your phone is archaeological dust. Your teacher today is Brother Thomas, whose claim to fame is that he once ruled an entire Bible in just under a year. The man is a human ruler. His lines are so straight that other monks use his practice sheets to check if their walls are perpendicular. He hands you a bone folder, a knife and a lead point. These are your tools. The knife isn't for defending the manuscript from Vikings, though that would be cool. It's for scraping mistakes off the vellum. The lead point is for marking incredibly faint guide dots that you'll connect to create your ruled lines. The bone folder is for making indented lines without marking the surface. Medieval engineering at its finest. The process goes like this. First, you calculate the text block dimensions. This isn't arbitrary. There are golden ratios involved, mathematical proportions that have been perfected over centuries to create the most visually pleasing and readable layout. The text block should be roughly 2/3 the height of the page and positioned according to geometric principles that Euclid would approve of. Brother Thomas shows you a manuscript from the early days of the monastery, before they understood these proportions. The text crowds the edges, like a teenager's first essay, trying to fill space with bigger handwriting. Then he shows you a recent production. The margins form perfect mathematical relationships. The inner margin is half the outer margin. The top margin is half the bottom margin. It's so satisfying your brain releases dopamine just looking at it. But here's where it gets really mathematical. The number of lines per page isn't random. It's calculated based on the specific text being copied. Mathematical proofs need more space between lines for annotations. Astronomical tables need precise grid patterns. Musical notation, yes, they're preserving that too, needs exactly parallel lines spaced according to mathematical intervals. Get the spacing wrong, and you've just invented jazz 700 years early. You start practicing on your wax tablet, making dots every 4 millimeters. Except millimeters don't exist yet, so you're measuring in barleycorns. 3 barleycorns equal 1 inch, which sounds insane until you realize it's actually quite accurate if you pick uniform grains. Medieval monks, solving problems with whatever's lying around since 500 AD, your first attempt at ruling is a disaster. Your lines look like a seismograph during an earthquake. Brother Thomas doesn't even critique it, he just sighs in a way that conveys deep spiritual disappointment. Your second attempt is better, if you squint and have very low standards. By your 50th attempt, you can almost make 2 parallel lines, progress. Meanwhile, the real scribes are dealing with problems that would break modern minds. Brother Wilhelm is copying a treatise on astronomy that includes star charts. These aren't just pretty pictures, they're mathematical diagrams accurate enough for navigation. Each star's position is calculated using spherical trigonometry that most college students today would struggle with. He's using a compass and ruler to place each point exactly where it needs to be, working from calculations that he's checking and double-checking against 3 different sources. One star in the wrong position, and ships could end up in Ireland instead of Iceland. Brother Francis is working on something even more mind-bending, a copy of Boethius's De Institution Arithmetica. This involves copying diagrams of number patterns that look like medieval fractals. Triangular numbers, square numbers, pentagonal numbers, all arranged in visual patterns that demonstrate mathematical principles. He's essentially creating infographics before graphics were info. Each dot has to be perfectly placed to maintain the mathematical relationships. It's like playing Cosmic Connect to the dots, where getting one wrong breaks the universe. The concentration in the room is so intense you could hear a flea sneeze. Nobody talks. There's actually a complex system of hand signals for communication. Tap your desk twice for more ink. Hold up 3 fingers for a bathroom break. Wave your left hand for a new quill. Point at Brother Marcus and shake your head when he starts humming again. It's like medieval sign language, except everyone's too focused to use it most of the time. Lunch break arrives, signaled by bells, because everything here is signaled by bells. You've been practicing ruling for 4 hours and managed to produce exactly 3 acceptable lines. At this rate, you'll be ready to copy actual text sometime around the next crusade. In the refectory, you sit in assigned seats that never change. The seating arrangement is based on seniority, specialty, and complex social dynamics that would make high school cafeterias look simple. The manuscript illuminators sit together, speaking in hushed tones about gold leaf techniques. The master scribes occupy the table nearest the lectern, where one lucky brother reads aloud during meals, because apparently eating in peace is a sin. Today's reading is from Bede's De Temporum Ratione, a treatise on calculating the date of Easter. This might sound boring, but it's actually one of the most mathematically complex problems of the medieval world. Easter is the first Sunday after the first full moon after the spring equinox. Simple, right? Wrong. This calculation involves lunar cycles, solar years, and a 19-year pattern called the Metonic cycle. Monks literally spent their entire careers working on algorithms to predict Easter dates centuries in advance. While you're choking down your daily bread and trying to follow the mathematical reasoning being read aloud, you notice something fascinating. The reader isn't just reciting the text, he's adding commentary, explaining the calculations in real time. This is how mathematical knowledge spreads through the monastery. Every meal is a math lecture. Every prayer service includes astronomical observations for timekeeping. You're living inside a giant mathematical organism that breathes calculations and sweats geometric proofs. After lunch, it's back to the scriptorium. The afternoon light is better, coming in at an angle that illuminates the desks perfectly. This is prime copying time. The senior scribes are racing against the sun, trying to complete as much as possible before the light fades. There's no working by candlelight, too risky for the manuscripts, and too expensive for the monastery. Candles are reserved for prayer and emergencies, like when Brother Edgar accidentally locked himself in the wine cellar and had to copy his way out. Long story. You're still practicing ruling, but now Brother Thomas adds a new element: margins. Not just any margins, mathematically proportioned margins that create harmonic relationships across the page spread. When the book is opened, the 2 inner margins combine to equal 1 outer margin. The proportions follow the golden ratio, 1.618 to 1, though they don't call it that. They call it the divine proportion, because everything here needs a religious name or it doesn't count. He shows you how to calculate these proportions using only a compass and straight, no measurements needed. It's pure geometric construction, the kind that would make Greek mathematicians cry with joy. You place your compass point at one corner, swing an arc, bisect the angle, extend the line, and suddenly you've created perfect proportional margins using nothing but circles and lines. It's basically magic, except it's math, which is honestly cooler. By the end of the day, you've successfully ruled one practice page. 1. It took you 9 hours to prepare a single page for text that hasn't even been written yet. At this rate, copying one mathematical treatise would take approximately forever. But that's exactly the point. This isn't about speed, it's about creating something that will outlast empires. Year 2 of your monastic adventure, and you've finally graduated from ruling lines to actual letters. Not words yet. Let's not get crazy. Individual letters. For the past 3 months, you've been practicing the letter ed exclusively, just ed. You've drawn approximately 10,000 letter. You dream about the letter ed. You see it in cloud formations. Your muscle memory is so programmed that you accidentally sign your name as Ed during confession, which Brother Theodore finds neither amusing nor appropriate. But today you're learning something special. You're being inducted into the secret world of medieval mathematical notation. Turns out copying mathematical texts isn't just about having nice handwriting. It's about understanding a symbolic language that's evolving in real time. Brother Adelard, who's become your mentor, mostly because everyone else gave up on you, shows you a Byzantine manuscript from the 9th century. The mathematical symbols look like someone sneezed ink onto the page. Then he shows you an Arabic text from the same period, completely different notation system. Same mathematical concepts. Your job, translate between them. While preserving the mathematical meaning, it's like being a UN interpreter for numbers. The Arabic numerals are just starting to trickle into European monasteries, and the confusion is real. Some monks think the symbol for 0 is a decoration. Others keep trying to add Roman numerals to Arabic equations, which works about as well as you'd expect. Brother Adelard shows you his personal notebook, where he's been developing a standardized conversion system. This man is basically creating mathematical Rosetta Stone, and nobody outside this room will ever know his name. The real challenge isn't just the numbers, it's the operational symbols: addition, subtraction, multiplication, division. None of these have standardized symbols yet. Some manuscripts use words, literally spelling out pluses and minuses in Latin. Others use abbreviations that vary from monastery to monastery. One place uses a cross for addition, another uses it for multiplication. It's chaos. Beautiful mathematical chaos. You're assigned to copy a simple arithmetic primer, simple being relative, because this primer includes long division of Roman numerals, which is like performing brain surgery with a spoon. The technique involves a counting board with columns for different place values, moving pebbles around like some demented accounting abacus. You have to translate this physical process into written instructions that someone could follow without the board. It's basically writing IKEA instructions for mathematics. Brother Adelard watches over your shoulder as you work, occasionally making sounds that could be approval or disappointment. It's hard to tell with him. His standards are impossibly high. A slightly curved line in a geometric diagram gets the whole page scraped clean. An inconsistent angle in a triangle means starting over. He once made Brother Francis recopy an entire treatise because the dots in his division notation weren't uniformly sized. The man has issues, but his manuscripts are perfection incarnate. The mathematical text you're copying includes word problems that would make modern students cry. A merchant travels from Rome to Constantinople, trading wool for silk at varying exchange rates calculated by weight, volume, and seasonal demand. How much profit does he make if the exchange rate fluctuates according to a geometric progression? Oh, and solve it using Roman numerals. Show your work, no calculators. Obviously, while you're struggling with merchant mathematics, Brother Wilhelm bursts into the scriptorium with news that spreads through the monastery like wildfire. A traveling scholar from Toledo has arrived with Arabic translations of Greek texts that were thought lost forever. This is like finding a new Beatles album in your grandmother's attic, except the Beatles are Aristotle and your grandmother is the Library of Alexandria. The entire monastery is buzzing. These aren't just any texts. These are mathematical works by Apollonius on conic sections, Diocles on parabolic mirrors, and rumour has it, fragments of Archimedes' method of mechanical theorems. This last one is huge. It's basically Archimedes explaining how he actually figured out his famous discoveries, like a behind-the-scenes director's commentary for mathematics. The abbot calls an emergency meeting. These texts need to be copied immediately before the scholar moves on to the next monastery. But here's the problem. They're in Arabic, translated from Greek, and they need to be rendered into Latin. It's a three-language mathematical relay race, and accuracy is everything. One mistranslation could set back mathematical understanding by centuries. You're pulled off your simple arithmetic primer to help with preparation work. Suddenly, you're part of the most important mathematical preservation project of the decade. No pressure. The texts arrive in the scriptorium like holy relics. They're written on paper, not vellum, which is still exotic and suspicious to most European monks. Paper from the Islamic world, made from cotton and linen, thinner than vellum, but somehow just as durable. Brother Adelard handles them like they're made of gold and spider silk. The first challenge is the diagrams. Greek geometry relies heavily on visual proofs, but the Arabic translations have adapted these to their own aesthetic style. The Latin versions need to be faithful to the mathematical content while being comprehensible to European readers. It's like translating a Japanese manga into English while keeping all the visual jokes intact. You're assigned to trace the simpler diagrams onto wax tablets, creating templates that senior scribes will use for the final versions. Your first diagram is a proof about the area of a circle. Seems simple enough until you realize the Arabic version uses a different approximation for pi than what European mathematicians are familiar with. Do you preserve the original value or adapt it to local understanding? These are the decisions that keep monks awake at night. Well, that and the 2 a.m. prayer bells. Brother Adelard makes the executive decision to include both values with extensive marginal notes explaining the difference. This manuscript is becoming less of a copy and more of a mathematical conference in book form. Every page has more commentary than original text, with 3 different monks adding their observations in microscopic handwriting around the edges. The collaborative effort is remarkable. Brother Conrad, the Vellum master, is preparing special sheets with wider margins for all these notes. Brother Heinrich is mixing a special batch of red ink for the commentary, distinct from the black main text. The kitchen staff, yes, even they're involved, are preparing extra rations because everyone's working through meal times. 3 weeks into the project, and the scriptorium looks like a medieval NASA control room during Apollo 13. Calculation tablets everywhere. Monks huddled in groups, arguing about geometric interpretations. Brother Marcus stress eating communion wafers in the corner. You've been promoted to actually copying simple sections of text, mainly numbering systems and basic equations. The responsibility is terrifying. Every stroke of your quill could preserve or destroy mathematical knowledge. You're basically performing intellectual heart surgery with a feather. The Arabic text includes something revolutionary: decimal fractions. Instead of the clunky Roman system of parts and portions, these Islamic mathematicians are using position-based decimals that make calculations infinitely easier. Brother Adelard is beside himself with excitement. He's already working out how to adapt this system for European use, creating conversion tables and practice problems. Watching the monks discover decimal notation is like watching cavemen discover fire, except these cavemen can already calculate eclipse predictions and architectural stress loads. They immediately recognize the implications. Suddenly, calculations that took hours can be done in minutes. Engineering projects that required teams of mathematicians might be managed by a single architect. It's a mathematical revolution happening in real time, in a freezing stone room by candlelight, in complete silence. The scholar from Toledo, Brother Gerard of Cremona, gives a lecture one evening about the translation process. He spent 20 years in Spain, learning Arabic specifically to access these mathematical texts. The man learned an entire language just to read math books. That's dedication that makes modern grad students look lazy. He explains how Arabic mathematical thinking differs from Greek. The Greeks were obsessed with geometric proofs, everything visual and spatial. The Arabids developed algorithmic thinking, step-by-step procedures that could be followed mechanically. Combine the two, and you get something entirely new. It's mathematical fusion cuisine, and it's delicious. Your contribution to this historic project. You've successfully copied 43 pages of basic arithmetic examples. It's not glamorous, but those examples will be used to teach the next generation of European mathematicians. Some kid in Oxford in 300 years will learn decimal multiplication from your handwriting. Your cramped, slightly crooked, occasionally smudged handwriting. The deadline approaches. The traveling scholar leaves in 3 days, and he wants to take copies with him to distribute to other monasteries. The scriptorium goes into overdrive. Monks are sleeping at their desks, taking shifts to maintain continuous copying. The kitchen sends food directly to the scriptorium. Chamber pots are strategically placed because nobody has time for bathroom breaks. It's like a medieval hackathon, except instead of creating an app nobody needs, they're preserving the foundations of mathematical knowledge. You make your first major mistake on day 2 of the crunch. While copying a geometric proof, you accidentally swap 2 angle measurements. Brother Adelard catches it during review, and the look he gives you could melt stone. The entire page has to be scraped clean and recopied. 4 hours of work, gone. You're relegated back to ruling lines as punishment, but honestly it's a relief. Less chance of destroying human knowledge with a misplaced digit. Year 3, and you've somehow become the monastery's unofficial expert on Arabic numerical notation. Not because you're particularly good at it, but because you're the only one who hasn't rage quit after trying to explain why 0 is a number and not just empty space. Today's assignment is your biggest yet, creating a teaching manual for the new novices arriving next month. The blind leading the blind, as Brother Adelard cheerfully puts it while assigning you this impossible task. The manual needs to explain place value notation to people who've only ever used Roman numerals. This is like explaining color to someone who's only ever seen in black and white, except harder, because at least colors are pretty. Place value is just abstract suffering with numbers. You start with the basics. In Roman numerals, xvad is 17 because x is 10, vad is 5, and ii is 2, and you just add them all up. Simple, intuitive, been working for 1,000 years. In Arabic notation, 17 is 17 because the 1 is in the tens place and the 7 is in the ones place. The position matters more than the symbol itself. Try explaining that to Brother Marcus, who's been doing monastery accounting in Roman numerals for 30 years, and thinks this new system is probably witchcraft. Your first draft includes helpful diagrams with columns labeled for place values. You draw little monks carrying numbers between columns to show regrouping in addition. It's basically medieval Common Core, and it's going about as well as you'd expect. Brother Francis reads your draft and immediately points out that your explanation of borrowing in subtraction makes no sense. How can you borrow something that doesn't exist? If you have 32 and subtract 15, where does the borrowed 10 come from? These are the philosophical questions that keep mathematical monks awake at night. While you're wrestling with mathematical pedagogy, news arrives that changes everything. The Fourth Crusade has gone spectacularly wrong, and instead of retaking Jerusalem, the Crusaders have sacked Constantinople. On one hand, this is terrible for Christianity. On the other hand, Byzantine manuscripts are flooding into Western Europe like intellectual plunder, morally questionable, absolutely, mathematically exciting. You bet. The monastery receives 3 crates of manuscripts from a knight who's having a crisis of conscience, and figures donating stolen books to monks might help with the whole eternal damnation thing. Inside are treasures beyond imagination. Complete copies of Euclid's Elements with commentary by Proclus, Ptolemy's Almagest with calculation tables for planetary motion, and the crown jewel, Diophantus's Arithmetica, the book that will one day drive Fermat crazy with margin notes. The abbot declares a day of celebration, which in monastery terms means slightly better bread and permission to talk during dinner. The scriptorium is reorganized completely. Your teaching manual is put on hold because every available scribe is needed for the preservation project. You're assigned to work on Ptolemy's star charts, which involves copying diagrams so complex they make modern subway maps look simple. The star charts are a mathematical nightmare wrapped in an astronomical puzzle, deep-fried in geometric complexity. Each star's position is calculated using a coordinate system based on celestial latitude and longitude, except the reference points are different from anything used today. You're essentially copying GPS coordinates for stars using a system invented 2,000 years before anyone knew the Earth was round. Well, educated people knew, but try explaining that to the local peasants. Brother Wilhelm, who's leading the Ptolemy project, explains that these charts aren't just for navigation, they're used to calculate astrological predictions, medical treatments, and agricultural schedules. Get a star position wrong, and someone might plant their crops at the wrong time and starve. No pressure though, just the lives and livelihoods of thousands of people, depending on your ability to correctly copy tiny dots on vellum. The mathematical principles underlying these charts are staggering. Each calculation involves spherical trigonometry that wasn't formally invented yet. Ptolemy worked out these relationships through pure geometric reasoning and observational data. He basically invented calculus concepts 700 years before Newton, but expressed them in geometric proofs that take 40 pages to explain what we now write in 2 lines of equations. You're copying a section on retrograde motion, where planets appear to move backward in the sky. Ptolemy's explanation involves epicycles, little circles on big circles, creating a mathematical model that's completely wrong but gives accurate predictions. It's like having the wrong formula, but getting the right answer anyway. The mathematical gymnastics required to make this system work would break modern computers. While working on these charts, you notice something interesting. Different manuscripts have slightly different star positions. Not errors, but systematic differences based on when and where the observations were made. The Arab astronomers updated Ptolemy's data with their own observations, creating a living document that evolved over centuries. You're not just copying a book, you're preserving an ongoing scientific conversation across cultures and centuries. Brother Adelard decides to add an innovation of his own. He creates a conversion table in the margins, showing how to adjust the star positions for the monastery's latitude. This is groundbreaking. He's not just preserving ancient knowledge, he's making it practical for contemporary use. It's the medieval equivalent of adding GPS coordinates to an ancient map. The work is exhausting. Each page takes days to complete. The diagrams require compass and straight constructions precise to fractions of a millimeter, fractions of a barley corn. Your eyes burn from squinting at tiny markings. Your back aches from hunching over the desk. Your fingers have permanent ink stains that make you look like you've been wrestling octopi. But something magical is happening. As you copy these astronomical calculations day after day, you begin to understand them. The patterns emerge from the numbers. The geometric relationships start making intuitive sense. You're not just copying mathematics, you're absorbing it through your fingertips, one carefully crafted symbol at a time. 3 months into the Byzantine manuscript project, and the monastery has transformed into a mathematical research institute. Monks who previously only cared about prayer schedules are now debating the finer points of geometric proofs. Brother Marcus, who couldn't understand place value to save his life, is suddenly fascinated by Diophantine equations. It's like watching your grandfather discover Reddit, confusing but oddly heartwarming. The collaborative effort has created something unexpected innovation. While copying these ancient texts, the monks aren't just preserving them, they're improving them. Brother Conrad noticed an error in one of Euclid's proofs that had been faithfully copied for centuries. After 3 days of heated debate that almost came to blows, scholarly blows, not actual punching, though Brother Francis looked ready to throw hands over the parallel postulate, they corrected it with extensive notation explaining the change. You're still working on star charts, but now with an additional responsibility. The abbot wants a simplified version for the parish priests who can barely read Latin, let alone understand spherical trigonometry. You need to create Astronomy for Dummies, medieval edition. This involves reducing complex calculations to simple rules of thumb. Instead of explaining the mathematical formula for planetary motion, you create charts showing which constellation each planet appears in for every month of the next decade. Your target audience is priests who think algebra might be a type of demon, so everything needs to be visual and intuitive. The simplified charts are actually harder to create than copying the originals. You have to understand the mathematics deeply enough to hide it completely. It's like being a magician who has to perform tricks while explaining there's no such thing as magic. Every simplification requires complex calculations on your wax tablets to ensure accuracy while removing complexity. Brother Wilhelm reviews your work with the expression of someone discovering their dog can do calculus. He's impressed but also slightly offended that you've reduced his beloved astronomical mathematics to picture books. Still, he admits the simplified charts will help spread astronomical knowledge beyond the monastery walls, which is ultimately the goal. The real excitement comes when Brother Gerard returns with more manuscripts, this time from Sicily. The Norman conquest of southern Italy has opened access to Greek manuscripts that bypassed the Arabic translation entirely, direct Greek to Latin translation, eliminating a layer of potential errors. It's like finding the original master recording after years of listening to bootleg copies. These new manuscripts include something extraordinary: Archimedes' work on the area of a parabola. His method involves exhaustion, basically proto-calculus, dividing the area into infinite triangles. The concept of infinity in mathematics is controversial. Some monks think it's heretical, since only God is infinite. Others argue that mathematical infinity is different from divine infinity. The debate rages for weeks, with theological and mathematical arguments flying back and forth like medieval Twitter beef. You stay out of the infinity debate, focusing instead on copying the geometric proofs. But even you can see the revolutionary implications. Archimedes is describing methods that won't be formalized for another 500 years. He's calculating areas and volumes using techniques that Newton and Leibniz will later claim to have invented. The guy was basically doing calculus before zero was even a proper number. Year 4 of your monastic career, and you've been promoted to something called a rubricator. Sounds fancy, but it basically means you're the guy who adds red letters to manuscripts. The medieval equivalent of a highlighter. Except if you mess up, months of work are ruined and everyone hates you forever. No stress. The red ink, called rubric, hence your fancy title, isn't just decorative, it's a sophisticated information system. Red letters mark important passages, new chapters, mathematical principles, and warnings about potential errors. You're essentially creating medieval hyperlinks, except instead of clicking, readers follow color codes that would make a modern UX designer weep with envy. Your current project involves adding rubrication to a newly copied text on mathematical optics by Alhazen or Ibn al-Haytham, if you're being culturally accurate. This Islamic scholar figured out how vision works, described the scientific method 400 years before it was cool, and solved mathematical problems that Europeans haven't even discovered yet. His work on optics involves geometric proofs about light reflection and refraction that require diagrams so complex they look like spiderwebs designed by an obsessive-compulsive mathematician. The rubrication system for mathematical texts is incredibly specific. Initial letters of theorems are large and red, proofs get smaller red capitals, corollaries are marked with red dots, errors discovered in transcription are marked with red crosses. Important calculations get red underlines. It's a whole visual language that took you 6 months to learn, and you still occasionally mark a theorem as a warning about heresy. Awkward, Brother Heinrich has created a special red ink just for mathematical manuscripts. It contains cinnabar, basically mercury sulfide, which creates a brilliant scarlet that will never fade. It will, however, slowly poison anyone who licks their fingers while working, which Brother Marcus learns the hard way when he starts seeing mathematical equations floating in his peripheral vision. Mercury poisoning, making math literally toxic since the 12th century. While you're carefully applying red ink to Alhazen's theories about parabolic mirrors, Brother Allard is having a crisis. He's discovered that 2 different manuscripts of the same mathematical text contain completely different proofs for the same theorem. Both proofs work, but they represent fundamentally different mathematical thinking. One is geometric, following Greek traditions. The other is algorithmic, showing Arabic influence. Which one should be preserved? The debate splits the scriptorium. Half the monks think both versions should be copied, creating parallel texts. The other half argue this will confuse future scholars. Brother Wilhelm suggests creating a composite version, but that's basically creating new mathematics, not preserving old mathematics. The philosophical implications are staggering. Are they preservers or creators, scribes or scholars? The abbot, in a moment of surprising wisdom, decides both versions should be copied with extensive commentary, explaining the differences. Future scholars can decide which approach they prefer. It's mathematical democracy, 700 years before democracy is cool again. Your rubrication work on Alhazen's optics leads to an unexpected discovery. While marking important passages, you notice that his mathematical descriptions of light behavior could be applied to improve the monastery's reading rooms. If mirrors were placed at specific angles calculated using his formulas, you could redirect sunlight to illuminate manuscripts, even in winter. You share this idea with Brother Conrad, expecting to be laughed at. Instead, he gets excited and starts sketching designs on his wax tablet. Within hours, half the monastery is involved in what becomes the Great Mirror Experiment of 1203. Monks are calculating angles, polishing metal sheets, and arguing about the reflective properties of different surfaces. It's like a medieval science fair, except everyone has tonsures and nobody's parents are forcing them to participate. The first attempt is a disaster. Brother Marcus places a mirror at what he swears is the correct angle, but instead of illuminating manuscripts, it creates a focused beam that nearly sets fire to Brother Francis's habit. Turns out concentrating sunlight using parabolic curves, which Alhazen describes in detail, creates what's essentially a medieval death ray. The military applications are noted and quickly suppressed, because nobody wants to explain to the bishop why monks are developing weapons. The second attempt works better, using flat mirrors and Alhazen's calculations for angle of incidence equals angle of reflection. You manage to redirect sunlight into the darkest corner of the scriptorium. It's not perfect. The light is dimmer than direct sunlight, but it extends the working day by 2 hours. In manuscript copying terms, that's huge. 2 extra hours per day means completing texts weeks faster. The success leads to a monastery-wide interest in practical mathematics. Suddenly, everyone wants to apply mathematical principles to daily problems. The kitchen staff uses geometric proportions to optimize bread baking. The gardeners apply Fibonacci sequences to plant arrangements, though they don't call it that yet. Even the gatekeeper starts using trigonometry to calculate the optimal angle for defending against Viking raids. Okay, that last one might be excessive, but the enthusiasm is infectious. Your rubrication work becomes more complex as you move to mathematical texts that include Arabic numerals alongside Roman numerals. The two systems need different colored inks to distinguish them. Arabic numerals get vermilion, Roman numerals get scarlet. It's a subtle difference that requires 2 different mercury compounds and probably takes years off your life expectancy, but the visual distinction helps readers navigate between numbering systems. Brother Adelard assigns you to rubricate his personal project, a comprehensive guide to mathematical notation across cultures. He's compiled symbols from Greek, Arabic, Hebrew, and even some Sanskrit sources that arrived through trade routes. Each culture developed different ways to express the same mathematical concepts. The square root symbol alone has 15 variations, each with subtle differences in meaning. Your job is to create a color-coding system that makes these differences clear without overwhelming the reader. The notation guide becomes the monastery's most ambitious project yet. You're not just preserving mathematics, you're creating a mathematical Rosetta Stone. Each page contains the same equation expressed in different notational systems, with color-coded explanations of the transformations. It's like Google Translate for mathematics, except every translation takes 3 days and might contain mercury poisoning. The complexity is mind-boggling. Some Arabic texts read right to left, including the mathematics. Hebrew texts do the same but with different conventions for numbers. Greek texts use letters as numbers, which seems efficient until you try to distinguish between alpha meaning 1 and alpha meaning the variable in an equation. Your color coding system becomes increasingly elaborate to handle these distinctions. You develop a standardized palette: vermilion for Arabic numerals, scarlet for Roman, orange for Greek letter numbers, rust for Hebrew notation. Variables get different shades depending on their cultural origin. Operational symbols are outlined in red with fills indicating their mathematical function. It's a chromatic nightmare that would make a synesthete cry, but it works. Other monasteries hear about the project and send representatives to learn the system. The scriptorium becomes a teaching center for mathematical notation. You, the person who couldn't copy a simple arithmetic primer 3 years ago, are now teaching master scribes from across Europe how to distinguish between Babylonian and Egyptian fraction notation using color theory. Life is weird sometimes. The guide reveals fascinating patterns. Every culture that developed mathematics independently came up with similar concepts, but expressed them differently. It's like mathematical convergent evolution. The concept of zero appears independently in Indian, Mayan, and Babylonian mathematics. The Pythagorean theorem is discovered separately by Greek, Chinese, and Indian mathematicians. The guide documents these parallel discoveries, creating a global history of mathematical thought. Brother Wilhelm points out that this guide could revolutionize how mathematics is taught. Instead of learning one system and being confused by others, scholars could see the underlying unity of mathematical concepts across cultures. It's mathematical Esperanto, except actually useful. The success of the notation guide leads to an expansion of your role. You're no longer just a rubricator, you're a mathematical translator. Merchants arrive seeking help converting between Byzantine and Islamic accounting systems. Engineers need Arabic architectural mathematics translated to Roman measurements. Even the local bishop wants help understanding astronomical calculations for determining Easter dates. You've accidentally become the monastery's mathematical consultant. The work is exhausting but exhilarating. Every day brings new mathematical challenges from different cultural traditions. You're preserving not just mathematical knowledge, but the diversity of mathematical thinking. Each notation system represents a different way of understanding numbers, shapes, and relationships. Some are visual, some algorithmic, some purely abstract. Together they form a complete picture of human mathematical achievement. Year 5, and the monastery receives news that will change everything. The Pope has authorized the creation of new universities in Paris, Oxford, and Bologna. These institutions need textbooks, specifically mathematical textbooks, and they're willing to pay actual money for books. The vow of poverty is about to get very complicated. The abbot calls a meeting that goes until midnight. The monastery could become the primary supplier of mathematical texts to these new universities, spreading knowledge while securing the monastery's financial future. But mass production means compromising quality. Instead of one perfect copy per year, they need dozens of good enough copies. It's the medieval equivalent of going from artisanal craft beer to Budweiser. And the senior scribes are not happy. Brother Adelard proposes a radical solution, the Pessia system. Instead of one scribe copying an entire book, the text would be divided into sections, Pessias, that multiple scribes could copy simultaneously. It's basically inventing the assembly line for book production. Henry Ford, eat your heart out. You're assigned to coordinate the mathematical Pessia system, mainly because you're one of the few people who understands multiple notation systems and can ensure consistency across different scribes. Your first challenge, dividing Euclid's elements into logical sections that can be copied independently while maintaining mathematical coherence. This is harder than it sounds. Mathematical proofs build on each other. Theorem 47 assumes you understand theorems 1 through 46. If different scribes make small errors that compound across sections, the final product could be mathematically nonsense. You need quality control procedures that would make ISO certification look casual. You develop a checking system. Each Pessia is copied by 3 different scribes. You compare all 3 versions, identify discrepancies, and create a master version. It triples the work, but catches errors that would otherwise propagate through dozens of copies. It's peer review, medieval style. The production rate is impressive. What previously took 1 scribe a year now takes a team 3 months. The monastery produces 15 complete copies of elements in the first year. Universities are placing orders faster than you can fill them. Suddenly mathematical education is accessible beyond the ultra-wealthy, its democratization of knowledge happening in real time in a freezing scriptorium by exhausted monks who haven't seen their families in years. But the rapid production creates new problems. Quality varies between copies. Rushed scribes make more errors. The simplified diagrams lack the precision of carefully crafted originals. You're mass-producing textbooks, but at what cost to mathematical accuracy? Brother Wilhelm has a breakdown when he discovers a rushed copy where pi has been approximated as 3, just 3, not 3, and a seventh, not 3.14, just 3. The mathematical horror of it sends him to the infirmary for a week. You implement stricter standards, but the pressure for production is intense. The Pessia system revolutionizes the monastery's operations, but it also creates a mathematical sweatshop. Scribes are working in shifts around the clock. The scriptorium, once a place of quiet contemplation, now resembles a medieval factory floor. The sound of scratching quills is so constant it becomes white noise. You develop repetitive stress injuries that didn't have names yet. Quill claw, ink finger, manuscript neck. The human body wasn't designed to copy mathematical proofs for 16 hours a day, but here you are pushing the limits of medieval ergonomics. To manage the increased production, you create specialized teams. The geometry squad handles all diagrams and constructions. The calculation crew focuses on arithmetic and number tables. The theory team tackles abstract proofs. It's mathematical specialization, turning generalist scribes into expert practitioners of specific mathematical subdisciplines. The geometry squad develops incredible skills. Brother Francis can draw a perfect circle freehand. Brother Marcus constructs regular polygons with 17 sides using only compass and straight. These aren't just copying skills. They're understanding geometry at such a deep level that it becomes intuitive. Watching them work is like watching mathematical jazz improvisation. The calculation crew becomes human computers. They develop mental arithmetic techniques that won't be formalized until the Renaissance. Brother Conrad can multiply 4-digit Roman numerals in his head by converting them to a mental abacus system he invented. The theory team is basically doing original mathematical research while copying. They're finding errors in ancient proofs, developing alternative solutions, and adding commentary that advances mathematical understanding. But the pressure is destroying them. Brother Thomas develops tremors in his hands from overwork. Brother Francis starts seeing geometric patterns when he closes his eyes. You yourself are having dreams where you're trapped inside an infinite recursion of copying yourself. Copying yourself. It's mathematical inception, and it's driving everyone slightly insane. The breaking point comes when a rushed copy of Al-Khwarizmi's algebra is delivered to the University of Paris with a critical error. A miscopied equation in the section on quadratic solutions means every problem in the book gives wrong answers. The university demands a refund and threatens to blacklist the monastery. The reputation you've spent years building could be destroyed by one careless mistake. Emergency quality control measures are implemented. Every mathematical text now requires 3 independent reviews. Calculations are checked using different methods. Geometric proofs are validated by physical construction. It slows production but prevents catastrophic errors. You're basically inventing mathematical peer review, quality assurance, and standardized testing all at once. The stress is affecting everyone differently. Brother Marcus starts an underground gambling ring based on who can copy the most accurate geometric proof fastest. Brother Heinrich begins experimenting with stimulant herbs to stay awake longer, basically inventing medieval Adderall. Brother Francis claims he's discovered a pattern in prime numbers but won't share it because he's saving it for his own treatise. The competitive atmosphere is toxic but somehow productive. The monastery's reputation recovers, but at a cost. 3 scribes have left, unable to handle the pressure. Brother Thomas's tremor is permanent. The infirmary is treating more repetitive stress injuries than plague symptoms. You've industrialized knowledge preservation, but the human cost is becoming evident. The abbot implements mandatory rest days, revolutionary for its time. Scribes can only work 6 days per week, with rotating Sabbaths to maintain production. It's basically inventing the weekend, though calling it that would be heretical. The rest days become crucial for preventing errors. Exhausted scribes make mistakes that cascade through mathematical proofs like dominoes. You realize that one scribal error in a geometric proof copied by students could miseducate an entire generation of mathematicians. The responsibility is paralyzing. To manage the psychological pressure, you introduce something radical: scribal signatures. Each monk signs their work with a unique mark, taking personal responsibility for their copying. It's accountability, but also pride. Suddenly, scribes are competing not just for speed, but for accuracy and beauty. Brother Francis develops an elaborate signature, incorporating a perfect golden spiral. Brother Marcus signs with a self-referential equation. Your own signature is simpler, just your initials in Arabic numerals, a small rebellion against Roman numeral supremacy. The signature system reveals interesting patterns. Some scribes are consistently accurate with arithmetic, but struggle with geometry. Others excel at theoretical proofs, but make calculation errors. You start assigning work based on individual strengths, basically inventing human resource management for mathematical copying. The specialization leads to innovation. The geometry squad develops new construction techniques that simplify complex proofs. The calculation crew creates standardized tables that reduce errors. The theory team writes commentary that clarifies ambiguous ancient texts. You're not just preserving mathematics anymore, you're advancing it. Orders from universities keep increasing. Oxford wants 20 copies of Ptolemy's Almagest. Paris needs 15 copies of Fibonacci's Liber Abaci. Bologna requests everything you have on Arabic algebra. The monastery is becoming medieval academia's Amazon. If Amazon was run by celibate men who wake up at 2 a.m. to pray, the success brings unexpected visitors. Scholars from across Europe arrive to study the monastery's collection. Merchants seek mathematical training for accounting. Even nobility send their sons to learn geometry for military fortifications. The monastery evolves from a preservation center to a mathematical university. You're promoted to Master of Mathematical Texts, a title that didn't exist until the abbot invented it just for you. Your responsibilities include managing production, maintaining quality, and training new scribes. You've gone from barely literate to running one of Europe's most important mathematical copying operations. Life is strange. The position comes with privileges. A private cell with an actual window, first choice of seats at meals, access to the restricted collection of texts deemed too dangerous for general copying. These include Arabic works on cryptography, Hebrew texts on mystical mathematics, and Greek writings on the mathematics of music that supposedly drive listeners mad. Year 6 brings a challenge nobody expected. A merchant from Venice arrives with something extraordinary: texts from China. Not just any texts, but mathematical works describing calculation methods unknown to both European and Islamic scholars. The Chinese use counting rods, a positional decimal system that predates Arabic numerals, and algorithms for solving equations that won't be discovered in Europe for another 300 years. The monastery explodes with excitement. Brother Adelard hasn't slept in 3 days, trying to understand the Chinese notation. Brother Wilhelm is constructing physical counting boards based on vague descriptions. You're tasked with creating a visual guide that translates Chinese mathematical concepts into something European scholars can understand. It's like trying to explain quantum physics using finger paintings. The Chinese texts include something called the 9 chapters on the mathematical art, though the merchant only has fragments. These fragments describe solutions to systems of linear equations using matrix methods, matrices. In the 13th century, while Europe is still struggling with quadratic equations, Chinese mathematicians are doing linear algebra. The cultural mathematics gap is humbling and exciting. Your translation work reveals fundamental differences in mathematical thinking. European mathematics, inherited from the Greeks, is obsessed with proof and logical deduction. Arabic mathematics focuses on algorithms and calculation methods. Chinese mathematics is about practical problem solving and pattern recognition. Each tradition has developed unique insights that the others lack. It's mathematical biodiversity, and you're documenting it all. The Chinese rod numeral system is particularly fascinating. It uses vertical and horizontal rods to represent numbers, with position indicating place value. It's essentially a physical computer for calculations. Brother Conrad builds a working model and demonstrates multiplication that's faster than any European method. The scribes watch in awe as he multiplies 5-digit numbers in seconds using little wooden sticks. It's basically ancient Chinese Excel. But copying these texts presents unique challenges. The diagrams showing rod positions don't translate well to European manuscripts. You need to develop new notation that preserves the mathematical meaning while being reproducible by scribes who've never seen Chinese characters. It's like creating emoji for mathematics before emoji exist. You develop a hybrid system using modified Roman numerals arranged in grid patterns to represent rod positions. It's ugly but functional. Brother Francis suggests using colors to distinguish vertical from horizontal rods, which works until you realize you'd need 17 different colors for complex calculations. Mercury poisoning is bad enough with 2 colors. 17 would kill everyone in the scriptorium within a month. The project takes an unexpected turn when the merchant reveals he also has texts on Chinese astronomy. These include star maps from a completely different perspective, literally, since Chinese astronomers are observing from a different latitude. The mathematical corrections needed to reconcile Chinese and Islamic astronomical data require spherical trigonometry that pushes everyone's abilities to the limit. The Chinese astronomical texts reveal something that shakes the monastery's understanding of mathematics. The Chinese have been recording supernovae for over 1,000 years, with precise mathematical descriptions of brightness changes over time. They're doing quantitative astronomy, while Europeans are still arguing about whether the heavens are perfect and unchangeable. Brother Wilhelm cross-references Chinese supernova records with Arabic observations and discovers they match perfectly when adjusted for geographical position. This is revolutionary. It proves that astronomical events are universal, visible from anywhere on Earth with the right calculations. The mathematical unity of the cosmos is confirmed by comparing notes between cultures that have never directly communicated. You're assigned to create a comprehensive comparison of Chinese, Arabic, and European star catalogues. This involves converting between 3 different coordinate systems, adjusting for precession of equinoxes, and accounting for observational errors. It's basically doing GPS calculations by hand, with quill and parchment, using mathematical techniques from 3 different continents. The work reveals that Chinese astronomers had calculated the length of the solar year to incredible precision. Their value is accurate to within minutes of modern measurements. They achieved this using mathematical techniques that involve tracking shadow lengths over centuries and calculating averages that account for leap years. It's statistical analysis before statistics was invented. While working on these conversions, you discover that the Chinese mathematical text includes a proof of what Europeans call the Pythagorean theorem, but dated 300 years before Pythagoras was born. The Chinese call it the Gogol theorem and use it for surveying and astronomy. This isn't just parallel discovery, It's evidence that mathematical truth is universal, discovered independently by every civilization that looks hard enough. The revelation sparks theological debates. If mathematical truth is universal, discovered by pagans and Christians alike, what does that say about the nature of divine revelation? Some monks argue that mathematics is God's language, written into creation for all to discover. Others worry this diminishes the special status of Christian knowledge. The debate gets heated enough that the bishop has to intervene. You stay out of the theological arguments, focusing on the practical challenge of copying mathematical diagrams that use Chinese characters as variables. Brother Adelard suggests substituting Latin letters, but this loses the visual patterns that Chinese mathematicians use for memorization. Chinese mathematical poetry, where equations are embedded in verse for easier recall, is completely untranslatable. You compromise by keeping Chinese characters with extensive footnotes explaining their mathematical meaning. The resulting manuscripts are bizarre hybrid documents, mixing Latin, Arabic, and Chinese notation. They're ugly but comprehensive, preserving mathematical knowledge from 3 continents in single volumes. Future scholars will need linguistic as well as mathematical skills to fully understand them. It's creating a new type of scholar, the mathematical polyglot. The Chinese mathematical texts include something that breaks everyone's brains: negative numbers used in actual calculations. European mathematicians acknowledge that debts exist, but using negative numbers in equations is considered absurd. How can you have -3 sheep? Chinese mathematicians don't care about philosophical objections. They use negative numbers to solve practical problems, and it works. You're tasked with creating educational materials to explain negative numbers to European scholars. This is like trying to explain why the Earth is round to flat earthers. Except the flat earthers are brilliant mathematicians who just happen to have a philosophical blind spot about numbers less than 0. Your approach is practical. You create word problems about merchants and debts, showing how negative numbers simplify calculations. If a merchant owes 5 gold pieces and earns 3, traditional European mathematics says he still owes 5 minus 3 equals 2. Chinese mathematics says he has -5 plus 3 equals -2. Same answer, but the Chinese method scales to complex transactions involving multiple debts and payments. Brother Marcus, the accounting expert, immediately sees the value. He starts using negative numbers in the monastery's financial records, creating the world's first double-entry bookkeeping system with explicit negative values. The abbot is initially suspicious but becomes a convert when Brother Marcus shows how it simplifies tracking the monastery's increasingly complex financial obligations to various universities. The integration of Chinese mathematics creates unexpected innovations. Brother Conrad combines Chinese rod calculus with Arabic decimal notation to create a hybrid system that's faster than either alone. Brother Francis applies Chinese geometric proofs to European architectural problems, designing a bell tower that uses 30% less stone while being structurally stronger. The mathematical fusion is creating practical benefits that even non-mathematicians can appreciate. Your role evolves from translator to mathematical ambassador. You're creating bridges between mathematical traditions, finding connections that nobody knew existed. The Chinese remainder theorem maps perfectly onto problems Fibonacci was exploring. Arabic algebra provides tools for solving Chinese astronomical calculations. Greek geometric proofs validate Chinese empirical formulas. It's mathematical globalization happening in a medieval monastery. The success of the Chinese project attracts attention from unexpected sources. Jewish scholars from Spain arrive with Hebrew mathematical texts including advanced combinatorics used for biblical analysis. Indian merchants bring Sanskrit texts on the mathematics of 0 and infinity. The monastery becomes a mathematical United Nations with you as the overworked translator trying to make everyone understand each other. The diversity of mathematical thought is overwhelming but exhilarating. Each tradition brings unique insights. Indians have been using decimal fractions for centuries. Jews developed probability theory for religious textual analysis. Every culture that develops mathematics finds different facets of the same underlying truth. You're documenting humanity's collective mathematical heritage. Year 7. And your life takes an unexpected turn. The University of Paris offers you a position as Master of Mathematical Studies. Leave the monastery, they say. Teach the next generation, have an actual salary. Sleep past 2 a.m. The temptation is real, but so is your commitment to the preservation work. You decline, but negotiate something better, a partnership where you remain at the monastery but create standardized curriculum for all European universities. The monastery becomes the medieval MIT, setting mathematical standards for higher education. Your first task is creating a graduated series of mathematical texts, from basic arithmetic to advanced astronomy. This isn't just organizing existing books, it's designing an entire educational progression. What concepts should students learn first? How do you bridge the gap between Roman and Arabic numerals? When do you introduce geometric proofs versus algorithmic methods? These decisions will shape European mathematical education for centuries. You design a 7-year program. First year basic arithmetic and number systems. Second year elementary geometry. Third year algebra and equations. Fourth year trigonometry and measurement. Fifth year astronomy and calendar calculations. Sixth year advanced geometry and conic sections. Seventh year mathematical philosophy and theoretical problems. It's basically inventing graduate school, medieval style. The curriculum requires creating new transitional texts. You can't jump from counting sheep to calculating planetary orbits. You need intermediate steps, practice problems, worked examples. You're essentially writing the world's first mathematics textbook series, except each textbook takes months to copy and costs more than a house. Brother Adelard helps develop something revolutionary, mathematical exercises with answer keys. Previously, students learned by copying and memorizing. Now they can practice and check their work. It's active learning, 700 years before education theorists claim to invent it. The answer keys are kept in a separate locked volume that only masters can access. It's basically creating teachers' editions, complete with medieval DRM. The curriculum design reveals gaps in available knowledge. European texts lack certain Arabic concepts. Arabic texts assume Greek geometric knowledge. Chinese methods don't translate to Western notation. You need to create supplementary materials that bridge these gaps, writing original mathematical content disguised as translation notes. You're secretly advancing mathematics, while claiming to just preserve it. The pressure to produce these educational materials is intense. Universities are accepting more students, creating demand for hundreds of copies. The monastery expands, recruiting scribes from other religious orders. You're training trainers, creating a second generation of mathematical scribes, who will spread across Europe. The copying operation scales beyond anything imagined when you arrived as an illiterate bankrupt. The Educational Standardization Project reveals a disturbing truth: mathematical knowledge is fragmenting. Different universities are teaching incompatible systems. Paris focuses on theoretical proofs. Oxford emphasizes practical calculations. Bologna teaches Arabic methods exclusively. Students transferring between universities can't understand each other's mathematical language. It's academic babble, and you're tasked with fixing it. You propose something radical: a universal mathematical notation system. One standard for all of Europe. The political implications are staggering. Getting French, English, Italian, and German scholars to agree on anything is like herding cats. If cats were arrogant academics with centuries-old traditions to defend, the negotiations take months and involve more diplomatic intrigue than most peace treaties. The compromise notation system is nobody's first choice, but everyone can live with it. Arabic numerals for calculations, Roman numerals for references, Greek letters for variables, Latin words for operations. It's a Frankenstein's monster of mathematical notation, but it works. Every university agrees to adopt it within 5 years. You've just standardized European mathematical education. The impact is immediate. Students can transfer between universities without relearning basic notation. Scholars can collaborate across borders. Mathematical discoveries spread faster because everyone speaks the same symbolic language. You've created the mathematical equivalent of the euro, except it actually works, and nobody's economy collapses. But standardization creates new problems. Regional mathematical traditions are being erased. Unique problem-solving methods, developed by isolated monasteries, are deemed non-standard and abandoned. You're preserving mathematics, but homogenizing it. The diversity that made Chinese mathematics so revealing is being sacrificed for efficiency. Brother Wilhelm raises ethical concerns. Are you preserving knowledge or controlling it? By deciding what's standard, you're determining what mathematics future generations will learn. The power is intoxicating and terrifying. You're basically the medieval Common Core, deciding mathematical education for millions of unborn students. To address these concerns, you create an appendix system. Standard texts are supplemented with regional variations, historical methods, and alternative approaches. It's like DVD extras for manuscripts. The main text teaches the standard method, but curious students can explore the rich diversity of mathematical thought in the appendices. These appendices become more popular than the main text. Students love learning multiple methods for solving the same problem. It makes mathematics feel alive, evolving, human. The Chinese rod calculus appendix is so popular that Oxford makes it a separate course. You've accidentally created mathematical multiculturalism. The success of the standardization project leads to an unexpected request. The Pope wants a definitive calculation of the date of Easter for the next 1,000 years. This is the Manhattan Project of medieval mathematics. Easter's date depends on lunar cycles, solar years, and ecclesiastical rules that make tax law look simple. Getting it wrong means the entire Christian world celebrates the resurrection on the wrong day. No pressure. You assemble a team of the monastery's best mathematical minds. Brother Adelard handles the astronomical calculations. Brother Wilhelm manages the lunar cycles. Brother Conrad deals with leap years and calendar corrections. You coordinate and try to prevent academic bloodshed when they disagree about computational methods. The mathematics involved is staggering. You need to account for the precession of equinoxes, the irregular length of lunar months, the drift between solar and lunar calendars, and ecclesiastical rules that sometimes override astronomical reality. It's like solving a 1,000-year weather forecast using an abacus. The team develops new mathematical techniques out of necessity. Brother Adelard creates recursive algorithms that generate Easter dates by pattern matching across 532-year cycles. Brother Wilhelm develops modular arithmetic techniques that won't be formalized for another 400 years. They're inventing number theory to solve a religious problem. The work takes 2 years. 2 years of calculations, verifications, and arguments about whether 2400 is a leap year. Spoiler, it is, but only because it's divisible by 400, not because it's divisible by 4. The rules are Byzantine, literally, since they come from Byzantine astronomical traditions. The final product is a massive codex containing Easter dates from 1200 to 2200 AD. Each date is calculated using 3 different methods to ensure accuracy. The margins contain the mathematical proofs, astronomical observations, and ecclesiastical justifications. It's not just a calendar, it's a mathematical monument. The Pope is so impressed, he grants the monastery special privileges, tax exemptions, land grants, and most importantly, exclusive rights to produce mathematical texts for all papal territories. You've turned mathematics into a medieval monopoly. The monastery is now the Microsoft of manuscript production, but with great power comes great responsibility. Other religious orders are jealous. Secular scholars claim you're hoarding knowledge. Universities complain about prices. You've created the first academic publishing controversy, complete with accusations of price gouging and monopolistic practices. The abbot navigates these politics while you focus on the mathematics, but the pressure is affecting everyone. To deflect criticism, you propose making basic mathematical texts available for free copying. Anyone can reproduce elementary arithmetic and geometry texts without payment. It's open source mathematics, medieval edition. Advanced texts remain premium products, funding the monastery's preservation work. It's a freemium model, 700 years before Silicon Valley claims to invent it. Year 8. Your final year, and everything changes with a single letter. Not a letter from the Pope or a university, but from your sister. Remember family? Those people you abandoned to become a monk? She writes that your nephew shows extraordinary mathematical talent, but the family can't afford education. Would the monastery consider taking him as a novice? The letter forces you to confront what you've become. 8 years ago, you were a mathematical illiterate fleeing bankruptcy. Now you're one of Europe's foremost authorities on mathematical preservation and education. The transformation is complete, but at what cost? You haven't seen sunshine that wasn't through a window in 3 years. Your hands are permanently stained with ink. You dream in equations. The abbot approves your nephew's admission, and suddenly you're responsible for training family. The boy arrives, 14 years old, bright-eyed, completely unprepared for monastic life. Watching him struggle with basic copying reminds you of your own beginnings. The cycle continues, but now your brother Adelard, the demanding master who accepts nothing less than perfection. Training your nephew reveals how much you've learned. You explain place value notation like breathing. Geometric proofs flow from your quill without thought. You casually reference Chinese calculation methods, Arabic algebra, and Greek geometry like old friends. The knowledge that once seemed impossible is now intuitive. You've become a living repository of mathematical tradition. But your nephew asks questions you can't answer. Why do we preserve these exact methods when better ones exist? Why copy errors faithfully instead of correcting them? Why maintain 3 different notation systems when one would be clearer? His fresh perspective challenges 8 years of assumptions. Maybe preservation isn't just about faithful copying. Maybe it's about improvement, innovation, evolution. The philosophical crisis coincides with practical changes. New technologies are arriving. Paper from the East, cheaper than vellum. Mechanical devices for ruling lines. Improved inks that dry faster and last longer. The manuscript production process that took you years to master is becoming obsolete. Do you resist change to preserve tradition, or embrace innovation to preserve more knowledge? You choose innovation secretly. While maintaining traditional methods for official manuscripts, you experiment with new techniques, paper drafts before vellum finals, mechanical aids for complex diagrams, standardized abbreviations that speed copying without losing meaning. You're hacking the medieval manuscript system, creating efficiencies that horrify purists but quadruple production. Your nephew becomes your accomplice in innovation. His young eyes spot patterns you miss. His questions reveal assumptions you didn't know you had. Together you develop new teaching methods that compress years of training into months. It's pedagogical revolution hidden within traditional preservation. The innovations you and your nephew develop spread through the monastery's younger scribes like wildfire. They're calling it the new method, though there's nothing really new about it, just optimizations of ancient techniques. But the old guard, brothers Adelard, Wilhelm, and Conrad, are not pleased. They see degradation where you see evolution. The conflict comes to a head when your nephew creates something unprecedented, a mathematical proof that synthesizes Greek geometry, Arabic algebra, and Chinese counting methods to solve a problem none of them could handle alone. It's brilliant, original, and completely unauthorized. Original work isn't preservation, it's creation. The monastery erupts in debate about its mission. Brother Adelard argues that creating new mathematics while claiming to preserve old mathematics is dishonest. Brother Wilhelm counters that all preservation involves interpretation, and interpretation is creation. The philosophical argument threatens to tear the scriptorium apart. You propose a solution that satisfies nobody but works for everybody: dual tracks. Traditional preservation continues unchanged, maintaining perfect historical fidelity, but alongside it, a new innovation track creates improved, synthesized, and original mathematical works, clearly marked as modern additions. It's basically forking the repository, medieval style. The dual-track system reveals something profound. The innovative texts are more popular with universities. Students learn better from synthesized materials than pure historical documents. The preserved originals become references for scholars, while the innovations become teaching tools. You've accidentally discovered that preservation and progress aren't opposites, they're complementary. Your nephew's success attracts other young talents. The monastery becomes a mathematical think tank disguised as a preservation center. New proofs emerge from the synthesis of old methods. Calculating techniques combine traditions from 3 continents. The scribes aren't just copying mathematics, they're doing mathematics. The transformation is remarkable. Brother Marcus, once confused by place value, is now developing new accounting methods. Brother Francis, who just drew pretty circles, is exploring non-Euclidean geometry 500 years early. Even Brother Heinrich, the ink master, is experimenting with chemical formulas that preserve different colors for mathematical diagrams. The monastery has become what it was always meant to be, not a museum, but a living center of mathematical thought. But success brings scrutiny. Church authorities question whether monks should be creating new knowledge or just preserving old wisdom. Universities complain that the monastery is competing with them for students and scholars. Other monasteries accuse you of abandoning traditional values. The political pressure is intense, and you're at the center of it. Your final months at the monastery are bittersweet. The abbot, recognizing the political pressure, suggests you take a pilgrimage. Not a real pilgrimage, but a diplomatic tour of European universities, sharing your preservation and teaching methods. It's exile disguised as honor, but you understand the monastery needs distance from controversy, and you've become too controversial to stay. Before leaving, you complete one last project, a comprehensive guide to mathematical preservation for future generations. Not just techniques for copying, but philosophies for maintaining living mathematical traditions. You encode everything you've learned, every innovation, every synthesis, every hard-won insight, from 8 years of obsessive dedication. The guide is structured like a mathematical proof. Axioms, why we preserve knowledge. Definitions, what constitutes mathematical truth. Theorems, methods for accurate preservation. Proofs, evidence that these methods work. Corollaries, innovations that emerge from preservation. It's your mathematical autobiography, disguised as a technical manual. Your nephew helps with the final copying, and you see your young self in his careful strokes. But he's starting further ahead, with advantages you never had. He reads Arabic, understands Chinese notation, thinks in multiple mathematical languages simultaneously. He's the future you helped create, a mathematical polymath born from preserved diversity. The farewell ceremony is surprisingly emotional. Brother Adelard, your harsh mentor, admits your innovations improved his own understanding. Brother Wilhelm gifts you a personal copy of his astronomical calculations, worth a fortune. Brother Marcus tears up, though he claims it's just ink fumes. Even Brother Heinrich creates a special ink just for you, a deep blue that will never fade, symbolic of permanence amidst change. You leave the monastery as dawn breaks, carrying nothing but knowledge. The gold you arrived seeking seems trivial now. You've gained something infinitely more valuable, the ability to read the mathematical language of the universe, written by cultures across space and time. Your nephew walks you to the gate, asking when you'll return. You don't answer because you don't know. The world outside needs mathematical knowledge, and you're one of the few who can bridge the gap between preserved tradition and living practice. As you walk down the road, you turn back once. The monastery sits solid against the sky, its scriptorium windows already glowing with candlelight. Inside, monks are beginning another day of preservation, innovation, and transformation. The work continues without you, but your influence permeates every stroke of every quill. You've helped preserve not just mathematical knowledge, but the living tradition of mathematical thought. The road ahead is uncertain, but your mathematical foundation is solid. Universities, courts, merchant houses, they all need what you know. You could teach, consult, or even establish your own copying center. The skills developed in monastic isolation are desperately needed in the wider world, but that's a story for another time. For now, you walk toward the rising sun, calculating its angle, appreciating its geometric perfection, understanding its astronomical significance. You're seeing the world through mathematical eyes, a perspective gained through 8 years of methodical, obsessive, beautiful preservation of humanity's numerical heritage. The end. Thanks for joining me on this mathematical journey through medieval monasticism. If you enjoyed this deep dive into the methodical preservation of mathematical knowledge, hit that like button and subscribe for more hidden histories. Drop a comment about what mathematical concept you think was the most important preservation, and remember, next time you complain about your math homework, at least you're not copying it by candlelight with mercury-poisoned ink. Until next time, keep calculating, keep questioning, and keep preserving knowledge for future generations. Peace out, mathematical warriors.